Okay, so in this set of slides, I'm going to explain in more detail generative networks. So here the idea is that we've seen a lot of techniques in this course for doing classification and also regression. But then another interesting question is a question of generation. Can we generate data? Okay, so yeah, again, so far, in our course, we had as input some data, and then the output was a class or a prediction in the case of regression. Right? So this was, we were in the realm of supervised learning, and then typically this is how we framed everything. Right? Now, it turns out that we can flip things around, and we can instead produce an output that is data as opposed to taking it as input. And this becomes interesting in various tasks. So for instance, in natural language, we've got natural language processing that is typically about, let's say, taking sentences or documents, perhaps categorizing them or extracting some information. But we also have natural language generation, where if you take a conversational agent or you're doing question answering or even machine translation, the output is essentially some text that needs to be generated, and that's effectively data, right? It's data in the sense that it's the same type of vector that we need to produce as what we would normally take as input in the other parts of natural language processing. Okay, and here it doesn't have to be just with respect to text. So speech is the same thing. So there's a lot of interest in doing natural speech synthesis. I mean, speech synthesis has been around for a long time, but in recent years it has improved a lot. And the main challenge is how can you make it natural? And the idea is that you would like to generate speech that sounds just like humans talking. And then even perhaps more challenging could be to generate images and also generate video sequences. And now we have some breakthroughs in that respect, thanks to various types of generative models that can generate fairly complex types of data that can correspond to also images and video. Okay, so now for this set of slides, the tasks that we're going to consider are effectively tasks where I'm going to generate a random vector. And then for each random vector, based on that, I'm going to try to produce some data that is realistic. And what I mean by realistic is that this data should be similar to perhaps data that I have in a data set. So again, like, let's say we have a conversational agent and it needs to respond to messages. Then in the same way that we as humans would respond to messages that people send us, then we would like the chatbot to also produce some output that generates text, and a human could not distinguish easily. It would think that it's another human that produces this output. Okay, so to do this, there's a lot of networks that have been proposed. So this is a partial list, but a while ago, Boltzmann machines were used for that, then sigmoid belief networks. Now, more recently, variational autoencoders and generative adversarial networks have become quite popular, and they are among some of the leading techniques for data generation. So today, these are the two types of networks that we're going to cover. There's more networks, and then next week, we're going to have a guest lecture by Priyank Jenny. He will talk about normalizing flows. So this is another type of neural network. This is very, very recent. Just been a few years that people have been developing these neural networks. And then they have some interesting properties as well that can be quite useful for generating data. Okay, so yeah, we won't cover all those types of networks. But today we'll talk about variational autoencoders and generative adversarial networks, and then next week, normalizing flows. Okay, so here it'll be useful for us to consider again probabilistic autoencoders and Again, the idea is that we have an encoder, which is a function f, but instead of being deterministic, we encode a conditional distribution to make it probabilistic. And then we do the same thing for the decoder. So the decoder is also a conditional distribution, but then we can think of the decoder as a form of generator, because what it does is it creates a distribution over data, so over x, and then in that sense it can be used to generate data. Okay, so here if we would like to use an autoencoder, a probabilistic autoencoder to generate data, then a simple approach could just be, let's sample some hidden representation h, and then after that sample some data point based on h. Right? So then we could use our decoder as a generator and then obtain some data. Okay, so for this to work, an important question is, what is this distribution P of h that we could use so that we obtain good samples and then we can apply our decoder? It turns out that we cannot use probability of h given x, because here it's conditioned on x, and if we already have x, it means we have already a data point, and then we're just going to be regenerating more or less that same data point. And here if we want to generate new data points, but new data points that will have the same properties as the data points that we have in a training set, then we would like to just get an h, but not make this h condition on x, so it should just be an h in general that's kind of similar to the h's that could be generated based on x, and then after that generate a data point based on that h. Okay, so one approach for doing this is known as a variational autoencoder. And here the idea is that we're going to sample h from a fixed distribution, a fixed Gaussian with mean 0 and variance 1. Okay, so essentially setting our prior distribution over h in this way. And now, if you look at the original work on variational autoencoders, there's some nice explanations about how we can think of this in the context of probabilistic graphical models. I'm going to skip those explanations, but just go straight to how they work and why they work. So here, to train a variational autoencoder, what we effectively do is we construct an objective that has a first part that essentially tries to maximize the probability of reconstructing x, or input x. And then we have a second part. You can think of it as some sort of regularization term. And what it does is it tries to make sure that our encoder has a distribution over h, conditioned on x, that is as close as possible to this fixed distribution, this fixed Gaussian with mean 0 and variance 1. The idea here is that I would like to be able to sample some hidden vectors h from this fixed distribution. Now, if my encoder produces a distribution over h that is far from the origin and maybe has large variance, it maps all of my data into some part of the space, but now I create some fixed distribution, and then this fixed distribution is in a different part of the space, then when I apply my decoder, I will not get good results. I need to make sure that these distributions are close to each other. And here again, I cannot sample directly from this distribution simply because this is conditioned on x, so I would automatically be reconstructing something similar to x, and I want something different. Okay, so just to illustrate, let me add a little bit to this picture that we've got on the board here. Okay, so here the intuition is that we have a probabilistic autoencoder. There's there's my input x, and then perhaps it comes from some space. Okay, so this is, let's say, my original data set, my training set. Okay. Then when I map this through, when I pass this through the encoder, if I sample from the distribution over H, perhaps it's going to map the data into some space that might have a certain shape like this. Okay? And then after this, so I guess, okay, here it means that there's a point that maps to this point, there's another point that maps to this point, and so on. So every point gets mapped to a different point here. And then finally, here I'm going to try to recover my original space. So roughly the same distribution. And then this point maps back to a point, and same thing here. Okay? So this is the idea behind probabilistic autoencoders. But now, you see, when I have my encoder that produces a distribution like this, if this is the distribution for my encoder, but then I have a fixed distribution that perhaps has the points elsewhere, like this, right? So this could be n of h given 0i, right? And this could be n of h given x mu sigma square. Okay, so you see, if these are different, then the problem is that when I map this with my decoder, it might end up into a different part of the space that doesn't correspond to my original data. So here, let's say that these points correspond to images that are faces. So what I'd like to be able to do is to generate as data out of my generator some more faces, as opposed to images of cars or birds or anything else, right? So here you see I'm going to generate images, but I want them all to be faces. So the problem is that when I sample from a fixed distribution, if this distribution does not correspond more or less to the distribution that I get from my encoder, right, then when I decode, I will get points that are also away from where the faces are, and I'm going to get instead images of a different type. Maybe I'll get images of cars and birds and so on. Okay, so I'd like to essentially make those to overlap as much as possible, and ideally to have the same shape. That's the intuition. Okay, so if we look again at our objective, the first part here, you can think of it as some form of reconstruction loss. So here, I'm going to maximize the probability that my network, this is my full autoencoder with the weights for the encoder F and the weights for the decoder G, right, are going to produce an X with high probability. So X is my input, so I want to be able to reconstruct X with high probability. So this is what we've been working with so far, but now I add an additional term, and then in this case, the intuition is that I want my encoder to have a distribution that is as close as possible to this fixed distribution that I'm going to use later to sample data points. Okay, so this is one intuition, and there's some mathematical derivation as well based on probabilistic graphical models to arrive at that I'm skipping here, but at least in terms of understanding what's going on, this should be sufficient. Any questions regarding this? Okay, let's continue. All right, so now the next question is, how can I optimize my network to essentially work with this objective, right? So I need to optimize my weights to maximize this objective. And okay, in principle, it's easy. I'm just going to do gradient descent. The trouble is that now I'm working with some probability distributions, and in particular, the first part of the objective, which is the reconstruction objective, if we expand this, mathematically, it would be equal to essentially taking the distribution of the encoder over h, and then for every h after that, having a distribution over x. But then I would integrate over all the h's that can be produced. And the problem is that this integral is not something that I can necessarily compute in closed form. Chances are, because my encoder and my decoder are complex neural networks, there's no reason for me to believe that there is a nice closed form solution to this integral. Okay, so most of the time it won't be something in closed form. So then I've got a problem, right? So this integral is not something I can compute. So now you see I've got a mathematical function. I want to compute the gradient of this, but there's an integral in the middle that I don't know what to do with it. Okay, so yeah, one solution for this, well actually, okay, yeah, we'll come back to this problem of h. Now let's look at the second term. So the second term will simply want the encoder to produce a conditional distribution that is close to a fixed Gaussian with zero mean unit variance. And we can write this down as follows. So first, since we want the encoder to be close to a Gaussian, then let's make the encoder as well produce a Gaussian. So if we want it to produce a Gaussian, it means that it's going to produce a vector of mu's and sigmas. These are the mean and square root of the variance. And these can be computed by little neural networks. So that's why here when I write mu n of xnwf, it means that I've got a neural network that produces the mean. Okay, so my neural network is not producing an h, it's producing a mean, and it's producing the square root of the variance. And then the idea is that I'm going to sample h from these things. Okay, so in fact this corresponds more or less to what I have on the board here. You see, I have x. This is my neural network that computes a mean mu and a square root of the variance sigma for every dimension of h. Okay, so that's how we would compute those two terms in the objective. But now, as I explained, computing this integral is something that is not going to be tractable in general, so we don't have a closed form solution. And then one idea is that we can simply sample to approximate this integral, right? So whenever you've got an integral, you can think of it as an infinitely large sum, right? So we're going to take essentially an average of samples. But now, to make things really simple in practice, we're going to do a drastic approximation. We're going to approximate our integral by a single sample. Okay, so now you might be worried about this, but it's okay, because even though it's a single sample that we're going to use, we're going to be doing many steps of gradient descent. Each time we're going to get a sample. So the idea is that we're still going to get lots of sample over our entire training process. Okay? But inside one iteration, then we're going to use a single sample. Okay, so if we approximate this by a single sample, what we can do is first produce an h by sampling from the encoder, and then simply approximate the resulting distribution by the distribution of the decoder. Any questions regarding this? Okay. All right, so just to make sure everyone understands, let me draw a picture that will illustrate now what really happens when we do the training. And here, what makes autoencoders a little bit different, I guess what makes variational autoencoders a little bit different than regular autoencoders is because they're probabilistic and there's a sampling step. We're going to have to be careful in our training so that we can still compute a gradient despite this sampling step. Okay, so for training, we have X. We're going to have some intermediate layers. Then we have here mu H, sigma H. Okay, and then from this, we're going to get an H. And then after this, we have some other intermediate layers. And then finally, we have X again. Or I guess let's just call it X tilde. Okay, so this is the idea where this is our encoder. This is our decoder. Okay, and when we pass an input through, right, we're going to end up with an X tilde. This X tilde, if I just go back to the objective, right, so here we would simply try to maximize the probability of X tilde according to this. Okay. Now, we would like to optimize this by gradient descent. The trouble is that if you look at this network, if you look at this network, I've got a sampling step. So here, when I wrote this tilde like this, it means that I'm sampling H from a distribution that has a mean mu H and a variance, or square root of a variance, sigma H. Okay? And the trouble is that, you see, when we compute a gradient, as long as we have a mathematical function that is continuous and so on, then I can compute the gradient. But if I've got a sampling step, I cannot compute the gradient easily. Okay, so here for training, we're going to have to use a reparameterization trick. And then in this reparameterization trick, we're going to change slightly the network so that we can sample and yet compute a gradient. So what we're going to do is have X again, have some intermediate layers, mu H, sigma H. Okay, so the encoder is the same. But now from this, we're also going to have, here I'll write H tilde, which is sampled from our fixed Gaussian. And I'm going to multiply those two. Then I'm going to add those two. So effectively, at this point, I've got H. And then I'm going to feed this into my other layers. And then I'll have X tilde. Okay, so here the key is that I'm introducing an H tilde. This one I'm going to sample it from my fixed Gaussian with mean 0 unit variance. And now I'm going to transform it to correspond to a sample H that would be coming from a different distribution. So this H, right, we want to think of it as coming from the distribution that has mean mu H, sigma H. Okay? And then so this is a simple trick. It's a reparameterization trick where what we can do is often when we want to sample from some distribution in a computer, what we do is we sample from a different distribution, then we do some operations on the sample until it becomes effectively a sample from the distribution that I was really interested in. So if I'm really interested in having a sample from this distribution, I can always sample from a Gaussian that has mean 0, variance 1, and then simply multiply by the variance, and then add the mean, and then I will get a result where now I have a value h, which is really a sample from this distribution. Okay? Now the benefit of doing this is that when I do gradient descent from here back to here, you see I now replace the sampling step that I had with some mathematical operations, so a sum and a product. I still have a sampling step here, but this is really an input now to my network. Okay, so it's okay to have some samples as long as the samples are inputs to the network, as opposed to being some value that's in the middle of the network. So here, h is a sample that is in the middle of the network. The problem is that I cannot compute a gradient backpropagate past the sampling step. Here, I can backpropagate all the way through here. I can also backpropagate back to h tilde. Now, h tilde is an input, so obviously I will not need to backpropagate further. So the fact that it got sampled is not a problem. Okay, so samples are okay as inputs, but they're not okay if they're intermediate values in the network. So that's what I'm illustrating here. Okay, any questions for this? So I guess, yeah, to summarize, then when we train, we work with this version of the network that has this reparameterization trick. And then we are optimizing this objective here, where we're maximizing the reconstruction of xn. And now we also have a regularization term that will ensure that our encoder has a distribution that is close to this fixed normal distribution. Okay, so we've now talked about how we do the training. Now, for testing or for generation, let's draw another picture that will illustrate now how we can use this network that we've just trained to generate an image, generate a data point. Okay, so testing in this case corresponds to generation. And in this case, we're only going to need the decoder. So we're going to start from H. Then we have some of those layers. And finally, we have X tilde. Like this. The idea is that now H is going to be sampled from our fixed Gaussian. And then once I have a specific value for H, I simply apply my decoder, and then I get a data point that, in principle, is going to be similar to the data points from my training set. And here you see, in our objective, we had the regularization term. If I just go back. Right, so I have this regularization term that minimizes the KL divergence. So KL stands for Kullback-Leibler. This is a distance measure for distributions. It turns out that for distributions, just using, let's say, Euclidean distance or some of the regular LP norms is often not appropriate. So there are other types of distance measures that are common for distributions. And one of the most popular one is this Kullback-Leibler divergence. OK, so the details of what that distance measure corresponds to are not too important. The point is that here we're simply trying to minimize the difference between our fixed distribution H our fixed distribution, which is Gaussian with mean 0 unit variance, and then our encoder distribution. So you see, when I use after that my decoder, because I trained my encoder to produce a distribution here that is close to having 0 mean unit variance, then it's okay for me to sample from this distribution and then produce a data point, because I will necessarily have some hidden representation H that are close to the real ones, and then when I apply the decoder, it's going to generate a data point similar to what I have in my training set. So if I want to get faces as output, then I'm likely to get an image that corresponds to a face thanks to this regularization term. Okay, any questions regarding this? Okay, very good. Okay, so we've now seen how we can train and also generate data. I've got here examples of images that were generated by a variational autoencoder. So on the left side, these are all human faces. You'll notice that those faces are a little bit blurred. At some level, it is normal, in part because here we have a probabilistic autoencoder, and the fact that I've got a distribution, it means that each time I run it, I might get slightly different pixel values, and then that's why the image is not sharp. Okay, so it's natural that I would get some blurriness in here, but still we can see that these are faces. They're just not with high resolution. We don't have to generate just pictures that are faces. I can do the same thing with digits. I can do this with any type of data. Okay. Any questions regarding variational autoencoders? Okay, very good. All right, so let's talk about another type of generative model that is quite popular in practice, known as generative adversarial networks. So these networks will in fact help us address the blur that we saw in those images. They're going to produce images that can be much sharper, and part of it is that they're not probabilistic, or at least they don't have an output that is probabilistic. Now, to train them, they have a very different and very interesting way of getting trained. So here, this approach is based on game theory. And the idea is that we're going to use two networks. We're going to have a generator, G, just like before. It takes as input some embedding or some hidden representation. In this call, I'm just calling it Z, but it's the same thing as H that we had before. But then we have a second network that we're going to call a discriminator. Now this network has nothing to do with an encoder, right? It does something completely different. Its job is to essentially predict whether some data point is real or not. And the way you can think of it is that in adversarial generative adversarial networks, the discriminator is essentially providing feedback to the generator. So when the generator produces a data point, it's a simulated data point. It's a fake data point because it got generated by the generator, as opposed to all the data points that we might have in a training set that are real data points produced by the environment out there. Okay? But now, if a discriminator can look at the data point generated by the generator and realize that, this data point is not, it doesn't have the same properties as the real ones, and I can tell that it's fake, that it got generated, then it's essentially providing feedback to the generator saying, okay, you're not doing a job as good as possible, right? I'm telling you that there are some properties I can pick on to realize that, yes, this is a simulated data point, okay? And then so we can think of the discriminator as providing feedback of that sort. And another way of thinking about it, it's a bit like, you see, as a student, wouldn't it be nice if you had a tutor with you who would essentially provide feedback about everything that you do continuously. So each time you're learning some concepts, right, you want to double check that you have a good understanding, and then your tutor would help you by continuously verifying that you understand well the concepts. So here we can think of the discriminator as this sort of tutor that will help our generator along the way. Okay, so those two networks are going to work together, but they're going to work in an adversarial way, in the sense that the generator is trying to generate data points that are as real as possible, and we could say that it succeeds when it manages to fool the discriminator in thinking that the data points that it generates are actually real. So if the discriminator cannot distinguish between the points generated and then the ones coming from our training set that are real, right, then at that point we could say that the generator is doing a great job, that it's generating points that the discriminator cannot distinguish, right, that are as real as those produced by the environment. Okay, so here we're going to do the training by setting an objective, and in this objective the generator is going to try to actually no, let's start with the discriminator. The discriminator is going to try to maximize the probability with which it can recognize data points from our training set as being real, and also it's going to try to maximize the probability that the data points that are generated by the generator are fake, right? So if it can distinguish between real data points and fake ones, right, then it means that it can still pick out some differences, and that's what it's going to try to achieve. Okay, so the discriminator is trying to maximize this probability of recognizing training points from our training sets as being real, and then points generated by the generator as being fake. Now, the counterpart of this is that the generator is trying to fool the discriminator. So in its case, it's going to try to minimize these probabilities, right? It's going to try to minimize the probability that the discriminator can recognize training points as being real, and it's going to try to minimize the probability that the point it generates are considered fake, right? So it wants to fool the discriminator in thinking that the points that it generates are real. Okay, so that's the objective. And here it's adversarial because you see the discriminator and the generator are essentially competing against each other. One is trying to maximize the objective here, and the other one is trying to minimize the objective. Okay, so in terms of optimizing this, we can simply rewrite this objective where here the probability that a data point is fake, I can rewrite this as 1 minus the probability that the discriminator thinks it's real. Okay, so here you see the discriminator produces a probability that a point is real. So if I want the probability that it's fake, I just do 1 minus that distribution. Okay, so that's the objective we're working with. Any questions regarding this objective? Okay. All right, so now let's see what the architecture of those two networks will look like and how we can do training as well as testing. So let's draw a picture. Okay, so I'm going to start with, let's just go back. So in this case, you see the generator takes as input z. So z is going to be some vector that is sampled from some distribution, and that's what we start with. So we feed in z, then we're going to have various layers that will eventually lead to x. Okay, so the generator is essentially producing some simulated data, and we denote this by x. Okay, so that's our generator, G. And then our discriminator, D, is going to take as input, so in fact, let me call this x tilde because this is generated. So it's going to take x and then produce just a bit. Where this bit here is essentially real, which could be 1, or fake, which could be 0. Okay, so the discriminator is effectively a classifier. Okay, so we essentially combine them in this way, but then we can also, for the discriminator, take a real x from our data set and then it would also produce a value, real or fake, on the real x. So here we have essentially one large network that combines the generator and the discriminator whenever we want to see what the discriminator is going to do with respect to simulated data. And otherwise, if we're using real data that comes from our training set, then we just need the discriminator. We apply it directly on x, and it's essentially the same architecture. Okay, so here, this is really the same as this, same weights, everything the same, just different inputs. So in our objective on this slide, you see when I compute d of g of zn, that corresponds to the bottom network that I drew right here. Okay, so this will produce a value of 0 or 1, indicating whether it's real or fake. And that's the output of this computation here. Now, for the probability that it's real, when it's a training point, then this part is just our top network that corresponds to the discriminator only, applied to x directly. Okay, so then we train this by backpropagation, compute the gradient, right? Take steps in the direction of the gradient to essentially optimize the subjective. But now we have two different set of weights, right? There's WD, WG. So we have, for the generator, WG. Here we have WD. And this is the same thing as well, WD. So we've got these weights. Now we need to optimize all of those weights, but some of them we want to optimize them by taking a step in the direction of the gradient, and others we want to optimize them by taking a step in the opposite direction of the gradient. Right? Because some cases we minimize, some cases we maximize. Okay, so here's an algorithm for training a generative adversarial network. Right? So in principle, it's as simple as just computing the gradient, taking steps in either the direction or opposite direction of the gradient. But now we need to be careful because we've got this min-max optimization. So one approach is to do the following. So we're going to have an outer loop where in this outer loop, we're going to have then an inner loop where we simply optimize the objective, well, we simply optimize the weights for the discriminator. And then we're going to do k steps of this. We're going to do many steps here. And then in contrast, we're going to do a single step for the generator. The reason for this is that if you look at the objective, the max with respect to WD is inside. So we need to essentially take a WG and then optimize WD for that. So that means we need to take many steps in the direction of the gradient to optimize WD with respect to a given WG. Once we've done that, then we can take a step in the opposite direction of the gradient to minimize the expression with respect to WG. And then after we've changed WG, then we need to re-optimize WD by taking many steps to make the expression as large as possible. So yeah, so that's the reason why here we have these two loops. The inner loops is with respect to WD because the optimization of the discriminator is inside the optimization of the generator. And then so we optimize this one. So here k steps, the idea is that in principle we would like to optimize fully the discriminator given the weights of the generator. In practice, these are iterative methods, so you have to stop at some point. So you often just take a large number of steps, k, and stop. Then you simply do one step to optimize the generator. And then for the generator, we descend with respect to the gradient, whereas with the discriminator, we go up with respect to the gradient. Okay, so this reflects our min-max optimization. Any questions regarding the algorithm? Okay, let's continue. Okay, so if you do this optimization, and let's say that everything works out nicely, what you're looking for is, in the end, to obtain a distribution for the generator that would correspond to the true data distribution. Right? So in the limit, you would like your generator to have a distribution over the space of data to be the same as the distribution that your training set came from. Right? So if you manage to get a generator that learns this distribution that was used to generate the training set, then the generator has succeeded. It will now be able to produce real data in the same way as the environment. And yeah, when it succeeds in this way, it will be impossible for the discriminator to tell whether a data point is real or fake, because if both the environment and our generator produce data according to the same distribution, then it's going to be impossible to distinguish their data points. So at that point, you see the discriminator will have a probability 0.5 of predicting whether a data point is real or fake. Right? So it should have a uniform distribution in terms of the prediction, or it should have a 50% error rate for that. So this is what we're looking for. This is what we're hoping to achieve. When things work out well, this is what we'll obtain. Now in practice, obviously, our generator is never perfect, so it's never going to completely fool the discriminator, and the discriminator is still going to have a probability that's higher than 50% of detecting whether points are correct or not. Now in practice, there are problems. One problem is that it's possible for a network to dominate the other. So here you see we have an adversarial setting. So the two networks are essentially one minimizing, the other one maximizing. And then you want to make sure that you see they are worthy opponents for each other, because otherwise it's a bit like, you see, let's say you've got a tutor who's helping you, okay, to learn some concepts, but let's say your tutor is no good and doesn't know anything about the material you're trying to learn. So you can completely fool your tutor in thinking that you understood the concepts, but your tutor cannot tell that. And really, you haven't learned anything still, and then when you write the exam after that, then you're going to do badly, right? So here, you see, we need a discriminator that is going to be good in terms of distinguishing. And the fact here that it has only 50% accuracy should reflect not so much that it's weak, but simply that the generator has succeeded. The problem is that in practice, you might achieve this where it's 50%, but it might just be because your discriminator is too weak. Okay, so that's one problem. And then there's also the problem that the generator might be too weak. So if the generator is too weak and it just cannot produce good data, then our discriminator might dominate and might just be able to tell perfectly what is real and what is fake. And then at that point, I guess, yeah, there is feedback being provided to the generator, but if the generator is too weak, it won't be able to use that feedback anyway. So in practice, it is difficult to obtain good results, in part because of you need a good balance between the strengths of those networks. The second problem is local convergence. So this is at some level no different than other types of networks. So when we're doing the optimization, here this is non-convex optimization. We might converge to a local optimum that is not as good and can be pretty far from the global optimum, and this will hinder the results. Okay, so yeah, so in practice, these tend to be important problems, and then in theory, you see the framework is beautiful. This should work, but in practice, it doesn't always work. Okay, so as some examples, so we've got here, again, digits and faces that are generated. If you look at the faces, they tend to be sharper, okay? And here we can generate all kinds of types of images. So at the bottom, we've got some more abstract images. Well, actually, no, they're not completely abstract. So there are some animals in here. They're just much more difficult images, but it still does a reasonable job. So here, okay, when you look at this, the right column where the pictures are highlighted, these correspond to the closest training points in our training set to the column right beside. So you see, this 9, this 0, this 2, and this 8 were generated by the generator. And now, to get a sense of how good these are in terms of data points, just as an exercise, we're plotting in this last column what is the nearest neighbor in the data set to show that indeed these are very close. They do correspond to points that are real, that are from our training set. Okay, in the case of digits, it's quite clear that we get a nearly perfect match. Now, for faces, you see we have, again, some faces that are generated here. They look quite real. And now we can see in our training set, there are other faces that have similar expressions. And, I mean, they're different. You can tell that these are not the same people, really, but they are still close, and that suggests that, yes, the network has learned to generate faces that are similar and yet different. Okay, so at the bottom here, we've got a horse. This is another animal, I think a dog. These images are a lot less clear, so there's still some blur in here. But if you look at the original images, they were also quite blur, and this is another example. Okay, any questions regarding generative adversarial networks? OK, so I guess this is it for today. So let's stop here. And yeah, next class we'll move on to another topic, so ensemble learning.